Welcome to Acoustics Derivations. In this video, we will be deriving the nonlinear wave equation for waves on a string, where the nonlinearity comes from finite deformation. On the left here, we have a schematic of the problem we are looking at. We have a string. Maybe I should change the color so you can see it. Here highlighted in orange. We have two tensile forces at the edge of our differential string element, delta S, which has components delta X in the X direction, delta C in the C direction, or the Y direction. And of course, we assume that the tensile forces are acting tangent to the differential element at positions X and positions X plus delta X. Now, we assume the string has a linear mass density rho sub L. We assume the tension T is constant, and we assume that elastic forces are neglected except for the fact that the string must be elastic enough to be extensible. Okay. With the setup out of the way, let's begin the derivation. So first we're going to appeal to Newton with some of the forces in the y direction, which is equal to the mass acceleration in the y direction. And what are the forces acting on our finite or infinitesimal rather string element? Well, it's just the tension, and it's tension acting at some angle t or some angle theta at x plus delta x, which is the vertical projection of tension. And of course we need to account for both sides of our element here. So we need to subtract off t sine theta because in our analysis here it's going downward. Okay. So then we note that the mass of the string is simply the mass density of the string times delta x for that's delta x for our element delta s. Also, we note that the acceleration in the y direction is simply the second derivative of position with respect to time, where c is the position. Okay, lovely. So we put everything together and we get rho L delta c delta t squared is equal to t times sine. I should say I'm moving delta x to the right hand side. I didn't mention that, but I should mention that. So t times sine of theta x plus delta x minus sine theta at x all divided by delta x. Okay. So now we're going to take the limit as delta x goes to zero. Well, the left hand side stays the same. Now the right hand side we have tension. Whoops. And then this here the sines divided by delta x and letting delta x go to zero. That turns out to just be the derivative of sine theta of x. Okay. So now we want to calculate what the derivative of sine of theta of x is with respect to x. And by that we need to use the chain rule, which of course is the derivative of some function. So we have a function which is a function of a variable, in this case, with respect to x, can of course be written as the outermost function with respect to g, so df dg, and then dg dx. Therefore, ddx sine theta of x, following this the chain rule, right? Chain rule is simply cosine theta d theta dx. So we can put everything together from here, or rather from here, put it together and substitute it in, and we obtain rho sub L d2 c dt squared is equal to t cosine theta d theta dx. And I'm going to label this star. Now, this is a perfectly valid equation. However, when we're deriving wave equations, we typically want, well, not typically, we always want the wave equation to be written in terms of a wave variable. And the only wave variable we have in this problem is c, not theta. So our wave variable is c. Not theta. So we need to figure out a way to turn cosine theta d theta dx into something pertaining to c. Okay. So first we can appeal to geometry. If I scroll back up here, we can see that looking at this triangle here, that delta x over delta x over delta s is equal to cosine of theta. Well, if you remember earlier in the problem, we took delta theta to going to zero. So we can note that dx is equal to cosine theta. And likewise, d c dx is equal to sine theta. So from geometry, we have that dx ds is equal to cosine theta, and d c ds is equal to sine theta. Okay. Well, simply dividing gives us tan theta of d c. D c dx. And I want to note here that I dropped the explicit dependence of theta with respect to x. Okay. So just note that that's what's happening here. Cosine of theta of x is really how it should be written, but I'm going to be writing theta a lot. So just note this dependence. Okay. Cool. So if you remember back to your trigonometry days, or maybe geometry days, we can know that 1 plus tangent squared theta is equal to secant squared theta. And then secant of theta is equal to 1 over cosine theta. Thus, 1 plus tangent squared theta is equal to 1 over cosine squared theta. Okay. Well, why am I doing this? Well, because if you remember, we have cosine theta here. But cosine is in terms of s, but tangent on the other hand is in terms of d c dx. And we want to be in terms of c. So we can rewrite this expression as cosine theta is equal to 1 plus tangent squared theta to the negative 1/2. Now we plug in that tangent theta is d cos c dx, and we obtain cosine theta is equal to 1 plus d cos c dx squared to the negative 1/2 power. So we have cosine of theta in terms of d cos c dx, which is what we want. Okay. So what about sine theta? Well, we can write sine theta as being equal to tangent of theta cosine theta, which by making the proper substitutions we can see is d cos c dx 1 plus d cos c dx squared to the negative 1/2 power. Okay. So now the next step is a little bit interesting. So just stick with me here. To eliminate where are we? The d theta dx in equation star. We're actually going to take the spatial derivative of cosine of theta. So d dx of cosine theta is equal to 1 plus d cos c dx squared to the negative to the negative 1/2 power. Okay. And that gives us negative sine theta, because remember theta is dependent on x, d theta dx, which is equal to negative 1/2 1 plus d cos c dx squared the negative 3/2 power times 2 d cos c dx d2 cos c dx squared. This is by the chain rule. I encourage you to try to prove this to yourself. Now these can cancel. Okay. So now we want to plug in our expression for sine into here, where it says sine. Also these minus signs will cancel. So there we go. So plugging in sine from above, we have that d cos c dx times 1 plus d cos c dx squared the negative 1/2 d theta dx is equal to 1 plus d cos c dx squared raised to the negative 3/2 d cos c dx d2 cos c dx squared. Okay. Well, this is very helpful because let me change colors for this. So we can cancel these terms. They're the same. This entire term makes this just negative 1. Thus, we can solve for d theta dx to be equal to 1 plus d cos c dx squared the negative 1 d2 cos c dx squared. Okay, lovely. And we note that this is in fact cosine squared theta d2 cos c dx squared. Okay, lovely. So recall. So now we have an expression for d theta dx as well as cosine theta. So remember what our equation was. We had rho L d2 cos c dt squared being equal to t cosine theta d theta dx. Let's plug the stuff in now. We have t 1 plus d cos c dx squared raised to the negative 3/2 d2 c dx squared which actually happens to be equal to t cosine cubed theta d to c dx squared. Now I prefer this one. This is more clear that it is nonlinear, but it's easier to see or to linearize using rather the second equation here. So this is our equation for finite deformations of a string, but suppose we then want to linearize to obtain the expression we obtained in the previous video, small deflection or small deformations of a string. So in the linear regime. Well, then we simply note the Taylor expansion of cosine theta, which is equal to 1 minus theta squared over 2 plus higher order terms, which is equal to 1 if the absolute value of theta squared is much less than 1. Again, this is a small angle. Then cosine cubed theta is approximately equal to 1, which gives us the linear wave equation for waves on a string, which is written here. And we note from previously, and I could have done this before, that we can write this in terms of C, where C is equal to the square root of T over rho sub L. So this concludes the derivation for nonlinear wave equation for waves on a string where the nonlinearity is due to finite deflections. Thank you.